Thank you for coming to this talk. My name is Junhyung Park, a PhD student at MPI Tübingen. The title of our paper is A Measure-Theoretic Axiomatization of Causality, and I was fortunate to work with Buchholz, a postdoc at the MPI, and my supervisors Bernhard Schölkopf, the director of our department, and Krikamol Muandet at CISPA Saarbrücken. The outline of the talk is as follows. The goal of our project is to propose a new axiomatic framework of causality, and we'll first give some intuition and motivation behind our ideas. In the second section, we'll give the basic abstract definition of the framework, and we'll proceed in the third section by presenting some concrete instantiations of it before we wrap up. Why is causality an important subject of study? Well, in many situations, studying correlation or association is not enough. In evaluating policies or drugs, for example, we need to study their treatment effect in a causal manner. In classifying these two images as cows, the picture of the cow is the causal cause of the label cow, rather than the backgrounds, which may also be highly correlated with the label. There are many other applications, areas such as law, blame, natural language processing, algorithmic recalls, transfer learning, out-of-distribution generalization, and many more in which causality features centrally. Our overall plan is to take probability theory as the starting point, but we recognize that probability theory is not rich enough to encode causal information, so we add interventional information to it to obtain what we name causal spaces. We first start by introducing probability theory, whose aim is to mathematize the concept of randomness or uncertainty or stochasticity, which on an intuitive level, humans have always had. The mathematical axiomatization of it that is almost universally taught and taken as the basis of research is the one provided by Kolmogorov based on measure theory. The fundamental object of this framework is a probability space, which is a triple omega HP, where omega is a set of outcomes, H is a sigma algebra of events, and P is a probability measure on these events. And I won't go through the axioms that these objects have to satisfy, but instead I'll take a step back and look at the big picture. So on the one side, we have a data generating process, and to study what kind of data is generated by it is the realm of probability theory. To go in the backwards direction, i.e. to start from data and infer things about the unknown data generating process, that's statistics. So statistics can be viewed as the inverse problem of probability theory. The field of causality was born from the observation that this picture does not have any causal information in it, so an enhanced view of the world looks like the following, where now the data generating process is endowed with causal information. In this paper, we focus solely on the force direction of the second picture. Our main idea is that if we view the second picture as an extension of the first, and given that there is a universally accepted framework of the first picture, then it should be a good starting point for an axiomatic framework of the force direction of the second picture. So we have to add something to probability theory, and that extra thing is interventional information. We view causality in essence as a study of what happens to a system when we intervene on a subsystem. If our system is a probability space, we're interested in what measures we get on the whole space when we intervene on subspaces of this probability space. So now we put all of this intuition into maths. First, let's introduce some notation. For a set T, we denote its power set by P of T. We'll take a product measurable space omega H with the index set T. For a subset S of T, we denote by H sub S the corresponding subsigma algebra. Intuitively, you should think of H as the entire space and H sub S as a subspace. The key object in our framework is what's called a transition probability kernel K sub S from these subspaces omega H sub S into omega H. And the important intuition behind these objects is that they're the same kind of objects as conditional distributions. They take two arguments, and once the first argument is fixed from the subspace omega HS, we have a measure on the whole space omega H in the second argument. Now we introduce the main definition. A causal space is defined as the quadruple omega HPK, where the first triple is simply a probability space, where omega H is in the form of a product as on the previous slide, and K is a collection of transition probability kernels K sub S, one for each subset S of T, that go from omega H sub S into omega H. We call these the causal kernels, and we'll come back to the two axioms that they have to satisfy. But for now, you should think of P as the observational distribution, i.e. the measure that we have on the whole space before any intervention takes place. We now define interventions. Given a causal space introduced on the previous slide, an intervention is a process of choosing a subset U of T and placing a measure Q on omega H sub U. Then we obtain a new causal space, and the causal kernel K sub U specifies precisely what new measure and causal kernels we will have in the new space. In particular, the intervention measure P do UQ is defined as the integration of the causal kernel K sub U by the measure Q that we place on the subspace omega H sub U. This corresponds exactly to the intuition that causality is a study of what happens to the whole space when we intervene on a subspace. Now we'll come back to the two axioms of causal kernels. The first axiom just tells us that intervening on nothing leaves the observational measure P intact. And the second axiom tells us that if we choose a subsigma algebra H sub U and intervene on it by giving it a measure Q, then the resulting measure on the whole space when restricted to H sub U coincides with Q. Now we give a series of concrete examples of causal spaces. The first is a classic example of correlation does not imply causation. We have two plots, first showing ice cream sales by month, and second showing accidents on the beach per month. And we all know intuitively why the plots show such a strong correlation. We also know that there is no causal relationship between the two. To represent this as a causal space, we take a two-way product of ice cream space and accident space. And P is a measure that has a strong correlation between the two spaces. The causal kernels are defined as follows. The causal kernel corresponding to ice cream, K sub ice, gives the same measure on the accident space as the observational measure for any value X of ice, representing the fact that ice cream sales do not have a causal effect on rip current accidents. Likewise, K sub accident is defined in such a way that for any value Y of accidents, the measure on the ice cream space stays the same as the observational measure. The next example is again a two-way product of rice yield and price of rice per kilogram. And without any intervention, we can suppose that the observational measure is such that the more rice there is in the market, the lower the price. The government can decide to intervene by buying up extra rice or releasing rice into the market from its stock with the goal of stabilizing supply at 3 million tons. Then the price will stabilize accordingly, though it won't be fixed deterministically since there are other factors that influence the price. And the corresponding kernel, causal kernel at rice equals 3 will be a measure that represents this. And for the sake of simplicity, we just let it be Gaussian. If instead the government fixes the price of rice at a high price, say 6,000 Korean won per kilogram, then the farmers might be incentivized to produce more rice. So the causal kernel K sub price at price equals 6 will again be a measure that reflects this information. You'll have noticed that what we've just had is a cyclic causal relationship, and cycles are notoriously hard to deal with in graphical structure causal models, but causal spaces can deal with cycles with no extra effort whatsoever. Finally, we give an example of a continuous time stochastic process, namely a one-dimensional Brownian motion. Now the causal space is indexed by the positive real line, and the observational measure is the Wiener measure. The causal kernels are specified to reflect the fact that if we intervene so that the process takes a particular value at a particular time point, then the Brownian motion starts again at that point. In particular, the past values causally affect the future, but the future values do not causally affect the past. And this is different to conditioning, represented on the right-hand plot, where if we condition on the process having value 0 at time 1, then the past values are affected since the process has to come back to that point. And continuous time stochastic processes have so far resisted formalization within existing causal frameworks, but the theory of stochastic processes is a well-established subfield of probability theory. And since causal spaces are built directly on top of probability theory, we can very naturally encode causal information to the theory of stochastic processes using causal kernels. Now we'll wrap up. So we've focused on the forwards direction of this picture and proposed causal spaces by endowing probability spaces with causal kernels. In the forwards direction, we believe that the value of a framework lies in its expressibility and generality, for which causal spaces excel over existing frameworks. In particular, causal spaces strictly generalize the interventional aspects of the existing frameworks, while overcoming some of their drawbacks, such as hidden confounders, cycles, and continuous time stochastic processes. In the backwards direction, assumptions are unavoidable. The value of a framework in the backwards direction should therefore lie in how well and naturally the assumptions can be encoded, And for that, existing frameworks such as the SCM or the potential outcomes excel. So I end the talk by stressing that our goal is not to criticize or replace existing frameworks, and rather is to complement existing frameworks. Thank you very much.